Hello everyone and welcome to lecture 5 of the Operations Management course. In this lecture, we are going to continue the subject of aggregate planning that we have started in the previous lecture. Today, we are going to have a look on the solution approaches to the aggregate planning problem. We will start by reviewing the formulation of the aggregate planning model. And then we will talk about a solution methodology which is called tabular graphical approach. Within this solution approach, there are some strategies that can be used, such as the uniform, the chase, and the mixed strategies. We are going to look at how these strategies are applied in the tabular graphical approach. And then we will talk about using a very nice tool which is Excel Solver for providing optimal solutions to the aggregate planning problem. And of course, in the optimal solutions, we look for the minimizing the total cost. So let us recall what we have talked about in the previous lecture. In the previous lecture, we started the topic of aggregate planning by describing the concept of aggregate unit of production. And we have seen in the previous lecture how to take the values of the forecasted demand for each individual product and then accumulate them together, combine them together to come up with the forecasted demand for the aggregate unit of production. And also in the previous lecture, we talked about a general formulation of the aggregate planning model in which we look for the relationships that govern the different decision variables involved and also how these decision variables are related to the problem parameters. And it's very important to note that the aggregate production planning structure presented in this course is not a general structure, and in real life you might find different variations in the structure of the problem itself. The structure that we are presenting in this course is used to demonstrate the basic elements and the basic concepts that are involved when we deal with the aggregate planning problem. Let us recall what we have talked about in the previous lecture. The given data for our problem, the aggregate planning problem, includes T, which is the number of planning periods, T capital, the number of planning periods. D sub T is the forecasted demand for period T, and that's of course for the aggregate unit. I sub node is the initial inventory that we have at the beginning of the planning horizon. Of course, the initial inventory for the aggregate unit. W node is the initial number of workers available at the beginning of the planning horizon. K capital is the number of aggregate units that can be produced by one worker in one day. And as I noted in the previous lecture, you have to recall exactly the units that we are using for describing the variable K. N sub T is the number of production days in period T. And usually when we study aggregate planning, the length of the planning horizon is usually 1 year, and T could be the index of the quarter, if you talk about 4 periods, or the index of the month, if we are talking about 12 periods within the planning horizon. And then when we multiply K by N sub T, this will give us the number of aggregate units that can be produced in period T by one worker. And this is a representation of the capacity per one worker. So if we multiply this result K times N sub T times the number of workers, this will give us the available capacity in period T. The decision variables that we are interested to find their values are W sub T, which is the workforce level in period T, which is simply the number of workers available. P sub T is the production level in period T. Of course, the production level will be restricted by the available number of workers. I sub T is the inventory level at the end of period T. B sub T is the backlogged quantity at the end of period T, which, as I mentioned, is something that you can think of as a negative inventory. So if at the end of the period, the total production that you had, in addition to any other available material at the beginning of the period, cannot cover the required demand in that period, this means you end up having a backlogged quantity. S sub T is the number of units subcontracted from outside sources in period T. H sub T is the number of workers that we are going to hire in period T. And of course, we assume that the training does not actually take long time. So when you hire new workers, they will be directly available for production. F sub T is the number of workers fired in period T. O sub T is the overtime production in units for period T. U sub T is the worker idle time in units, which is we call the undertime in period T. We talked about the different types of costs that are involved in aggregate planning, and these include C sub H, the cost of hiring one worker, C sub F, the cost of firing one worker, C sub I is the cost of holding 1 unit of stock for one period, which is sometimes called the inventory holding cost. C sub B is the cost of backlogging 1 unit of stock for one period. Okay. C sub S is the cost of subcontract 1 unit of production. C sub R is the cost of producing one unit on regular time. C sub O is the incremental cost of producing 1 unit on overtime. C sub U is the idle cost per unit of production. So these are the cost elements. Of course, when we formulate the aggregate planning problem, the main objective is to minimize the total costs that will result from the plan that we are developing. So sometimes, okay, a company might wish to consider other objectives, okay, but the most commonly used objective is to minimize the total costs. The governing equations that govern the relationships between the decision variables and the different problem parameters are given as follows. First, we have a relationship that relates the number of workers in a given period with the number of workers in a previous period, in addition to the number of workers hired and fired. So this equation is actually repeated for all periods, where of course T is the index of the period, which equals 1 to up to T capital. The second equation is the production quantity. Here, the amount of production, okay, that's the quantity that we are going to produce, equals the total available capacity in period T, expressed in terms of the number of workers. That is multiplying W sub T, which is the number of workers available in period T, by K N sub T. This will give us the total production capacity available in period T. Now, sometimes we decide to produce that quantity exactly, and sometimes we might add to that quantity some production during overtime. That's why we add O sub T here. Now, sometimes also we may decide not to use the full capacity given in this term, but actually we use less than this capacity. So we need to express that using the variable U sub T, which represents the under time in the number of units that we did not produce during period T. And of course, this equation will be repeated for all other periods from 1 to T capital. The third equation is called the inventory balance equation. And as you can see here, we already discussed it in the previous lecture. Okay, I sub T is the inventory at the end of period T. B sub T is the backlogged quantity, okay, in the number of aggregate units, of course, at the end of period T. The difference between both values, and remember, all variables in our model should always be non-negative. So here, okay, when this term in the left-hand side is negative, this means what? This means we have backlogged quantity at the end of period T, okay? If it is positive, then this means we have inventory quantity at the end of period T. If it is 0, this means what? This means we neither have inventory nor backlogged quantities. Okay. The left-hand side term is related to the situation at the end of the previous period, which is the difference between the inventory at the end of the previous period and the quantity backlogged at the end of the previous period. And then during period T, we add or subtract from the inventory this quantity, which is simply the amount of production, the quantity that we will decide to produce, plus the amount that we are going to subcontract in period T. And of course, the summation of these two terms will give us what? Will give us the total quantity that will be made available during period T. And then we subtract from that the demand in period T. And of course, this is the forecasted demand for the aggregate unit. And of course, again, this equation will be repeated for all indices T from 1 to T capital. So this is called the inventory balance equation. Finally, we have a very important condition, which is called the non-negativity constraint or condition. Okay, all the equations that we have presented earlier will not be valid unless all the decision variables are non-negative. Now, let us briefly describe the concept of the tabular graphical approach. It's basically an outline of what we shall do in order to provide a solution to the aggregate planning problem. And by a solution, we mean values for the decision variables that will actually guide us on how to plan for aggregate production. The tabular graphical approach is very simple, systematic approach. It starts by determining the demand for each period. And of course, here the demand is the aggregate demand value for each period. That's the first step. Then determine the capacity for regular time, overtime, and subcontracting in each period. So it's like we start by the demand. Okay, we take the demand values based on the demand values, we come up with estimates for, well, what would be the amount of uh, capacity or the total production that needs to be available during regular time. Do we need some overtime production, or do we need some contracting for other units? Okay. And then in the next step, we, based on our solution, we find the associated costs of our solution: labor costs, hiring and laying off costs, and inventory holding costs. Okay. When we decide about the production capacity, which will be governed by the number of workers, we have to take into consideration the company policy on how workers will be hired or fired, the company policy regarding the stock levels. Some companies might wish to have safety stock, for instance. Some companies might have restrictions on backlog demand. It may not be accepted, or it can be accepted with certain level, and so on. Those policies can affect, of course, the decisions that we will make. And then what we will do is we will develop alternative plans and examine their total costs. So it's like we should have some different alternative plans generated. And of course, the generation of these plans will be governed by the company policies, and of course, they will, in order to facilitate the calculations, we will use some strategies for generating the alternative plans. Those strategies include what's called uniform strategy. This is a solution strategy in which we provide a solution to the aggregate planning problem in which we maintain a constant workforce level throughout the planning horizon. So it's like in this policy, we would like to maintain a fixed capacity level for the regular time production, okay, by fixing the number of workers. And of course, in this case, when we keep constant workforce level, this means what? This means we will not have neither hiring nor firing, except probably for the first period. Okay. And when we do that, actually, in some periods in which the demand is higher than the available capacity, we might decide using subcontracting or overtime production to fulfill the required demand. Or probably we can have some backlog demand from one period to another. The second strategy is called the chase strategy. And it's another extreme solution in which we have a no inventory plan. No inventory plan means, okay, our production capacity should always be matched with the required demand. So it's like in each period, what I'm going to do, I'm going to look at the total demand required, and based on the total demand, I'm going to decide either I will hire more workers to achieve that demand, or fire some workers to reduce my production capacity if I don't really need to have that capacity, depending again on the amount of demand that we have. Okay, that's why it's called a chase strategy. It's like the capacity is chasing the demand. Now, these two strategies, as I said, represent two extremes of the solutions that we can generate for the aggregate planning problem. Between them, we have a third strategy, which is called a mixed strategy. In the mixed strategy, we might wish to maintain a fixed workforce level for a specific number of periods. Like if you have 12 months planning horizon, you might wish to consider, for instance, fixed capacity in the first 4 months, and then we will change the capacity at the end of the fourth month and maintain it for the next 4 months and so on. So it's like you have a mix between chase and uniform strategies. Of course, we are going to have an example on how to actually solve using these three strategies. Now, the idea of the tabular graphical approach is represented by using either a table or a graph. And as you can see here, if you have a graphical representation of the cumulative demand in terms of the number of aggregate units, okay, and you draw this cumulative demand, as you can see here, this curve actually represents the cumulative demand for the aggregate units. Of course, these are based on the demand information that is made available by forecasting. Now, throughout the planning horizon, which is represented on the abscissa, so it's here, these points represent the end of periods within the planning horizon. We monitor the changes that will happen to the cumulative demand. And an easier approach to do here is at the end of the planning horizon, let us say this point, okay, we have a cumulative demand value, let us say 6,000 aggregate units. Now, if you connect the origin point 00 here with this point, this will, of course, the connection here is done by a straight line. This will give you what's called the cumulative level production, which is something that you will obtain when you apply the level strategy, because in the level strategy, the number of workers are fixed, so the production capacity is fixed throughout the planning horizon. So in this case, if the production capacity is fixed, okay, what you will get here when you represent the cumulative quantity produced throughout the planning horizon, you get this straight line. Now, as you notice here in this example, there are some periods in which the cumulative forecasted demand, okay, has values that are lower than the cumulative production capacity level. Okay, and there are some periods in which the opposite happens. So during these periods in which the production capacity is higher than the forecasted demand, okay, and of course we are talking about cumulative units, this means what? This means you are in a situation in which you have excess production, and this will be transformed into excess inventory. Okay, so what happens here during these periods, okay, the first 4 periods here, you will start accumulating inventory because your production is higher than the demand. Now, after that, you will start to see the opposite happens, as I said. So the cumulative demand will be higher than the cumulative production capacity. And that's the period in which you start taking from the inventory that you have built up in the previous periods. So this actually illustration gives you an idea about the tabular graphical approach. It's basically based on the concept of comparing the cumulative forecasted demand with the cumulative production capacity, and what you are trying to do is you are trying to see, well, what will be the periods in which we are going to keep inventory, in which periods we are going to have subcontracted quantities, or we can just withdraw the quantities that are made available in inventory, and so on. Of course, if you are applying a chase strategy, for instance, for this problem, what happens is you would look for the cumulative demand curve and try to match the production quantities or the production capacity with this curve. So in a chase strategy, you might find your curve, the cumulative production curve, is actually coinciding with the cumulative forecasted demand. And of course, these are the two extreme cases, as I mentioned. Okay, because we have actually, in addition to the production capacity, in regular time, we might have overtime production, we might have subcontracted quantities. Okay, all right. Now, let us see an example on how to apply the tabular graphical approach and, and how to use the solution strategies that we talked about. In this slide, I present a very simple example. Okay, as you can see here, we have the demand information given over 12 months planning horizon, and we have the values of the requested or the demanded quantities. And again, remember, these are the aggregate demand units. And we also, the first step, usually we calculate the cumulative demand for each period. So the cumulative demand is calculated by summing up or accumulating the demand values. So here we start with 16, and then 16 plus 14 becomes 30, 30 plus 15 is 45, and so on. And at the end, we reach this value, which is 240. Okay, this number represents what the total production quantity that are needed based on the forecasted demand for the aggregate unit of production. We need further information in order to build our model and start applying our solution strategies and assessing them. The other information that we have here is each unit requires 40 man-hours to produce. Okay. Each employee contributes 150 hours per month. Now, no overtime is allowed. So that's specific to this problem. Okay, overtime is not allowed. That's the company policy. Okay, so this means what? This means we do not have any overtime production quantities. And we should actually always depend on regular time production, or we might wish to subcontract some quantities if that's permitted. No scrap or rework is assumed. Yeah, this is just an assumption that the production capacity that you will have will give you the required quantities 100%. Okay, 100% of time. So this means all the production quantity will be used. All the production capacity will be used. It costs 3,000 Egyptian pounds to hire an employee and 5,000 Egyptian pounds to lay off. It costs 20 Egyptian pounds to hold 1 unit of inventory per month. That's the C sub H, which is the inventory holding cost. Regular time production cost is 650 pounds per unit. So each unit that you are going to produce will cost you this amount. An item can be subcontracted for 800 Egyptian pounds. So this means in this problem, subcontracting is allowed. So the decision variable associated with subcontracting, which is denoted S sub T, can have non-zero values. The undertime cost is estimated as 50 Egyptian pounds per hour per worker. Okay, remember the undertime cost is the cost associated with not using the full capacity that you have. Okay, and of course, I mean this number. Okay, when we use this number, which is 50 Egyptian pounds per hour per worker, we might need to convert it into the correct units that we are going to use in the model. Why? Because actually in our model, we have to, I mean, this cost, the undertime cost, C sub U, is defined per unit of production, not per hour per worker. So somehow we need to convert this number. No shortage is allowed, another policy of the company. Okay, so this means no shortage means you are not allowed to have any backlogged quantities in any period. Backlogging is not allowed. So it should always be zero. Finally, initially there are 5 workers. So this is the initial condition that we have, 5 workers, which means W naught is 5, and nothing is kept in inventory and no back orders. So this means at the beginning of the planning horizon, okay, we do not have any inventory kept, and we do not have any backlogged quantity from the previous planning horizon. So these are the starting conditions for solving this problem. Now, as I mentioned, the first step that we have is we have to compile the data that we are given in the problem statement, and compiling it means finding the values of the parameters, okay, with the correct units so that they can be used within our model easily and of course within our solution approach. So here what I'm doing is, well, let us calculate production man hours per unit equals 40. Number of monthly working hours per week, 150. Okay, so of course, this is given information and we assume that this will be fixed for all periods. Okay, now K times N sub T, okay, needs to be calculated. And in our case, it's 3.75, which means one worker can produce 7.5 units in each period. Cost of hiring a worker, cost of firing a worker, they are already given. Inventory holding cost, regular time production cost, subcontracting cost per unit, undertime cost, and idle cost. Now again, remember this idle time cost is 50. Okay, remember we need to use the correct units. Okay, it's 50 per hour per worker. Okay, so remember we need to use the correct units when we do our calculations. So as you can see here, okay, using this number, which is 50, the undertime cost per hour per worker, okay, we multiply by 40, which is the production man hours per unit. This will give us the equivalent idle cost per unit of production, which is C sub U, which we need to use in our model. Now, let us see how these calculations or these numbers can be used within the level strategy, the chase strategy, the mixed strategy, through I'm using this the numerical data using Excel, Microsoft Excel. So here I have entered all the problem data on Excel, as you can see here. Okay, these are the values that we have in our problem, given problem data. Okay, as you can see here, this 3.75 is calculated by dividing the number 150 by 40. This will give us the K times N sub T. And then the other parameters are given here. As you can see, the last parameter is actually the multiplication of 40 by 50, which is C sub U, the cost of idle unit of production. Now, in the level strategy, okay, what you need to do is you need to maintain a uniform capacity throughout the planning horizon. And by uniform capacity, we mean fixed number of workers. This is how we interpret the concept of uniform capacity or level capacity. So in order to come up with this number, we need to calculate first what is the average monthly demand. The average monthly demand is simply the summation of the demand values given in our table and dividing it by 12. This will give us the average monthly demand, which is 20 units. So this means, okay, if I'm planning for a fixed workforce, then I might need to use this average monthly demand value to estimate the production capacity level, which is represented by the number of workers. Now, if you have or if you need 20 monthly units of demand, this means the required man hours can be calculated. Required man hours here is simply the multiplication of the production man hours per unit times the average number of units. So this will give us the required man hours per month on average, which is 800 man hours. Now, if you divide 800 by the number of monthly working hours per worker, which is assumed to be fixed for all periods, then what you will get is you will get the number of workers that you will need to have in order to fulfill the required demand. Okay, on average, everything here is calculated on the average value. Of course, the number may not be integer value, such as the case that we have here is 5.333. So this means what? Well, this means you have to approximate it. And of course, we take the nearest higher integer. Okay, that's the number of workers that we would like to maintain fixed throughout the planning horizon that we have in our problem. Now, it's mentioned in the given data, okay, here that the current number of workers is actually 5. So what I'm doing here is I'm building a table. Okay, this table actually includes all the problem data in addition to the decision variables that we wish to find their values. We start with, of course, the index of the period, and we also next column is the total, or actually the monthly demand. And then we start up with W sub t, which represents the decision variable, which is related to the number of workers in period t. Again, we start up our plan with 5 workers available. So this means what? This means, okay, in order to maintain a fixed number of workers, of 6 workers throughout the planning horizon, we need to hire 1 worker in the first month. Okay, and of course, throughout the remaining months, we will not have any hired or fired workers because we would like to maintain that fixed level of production capacity. Now, based on this fixed number of workers, okay, we can calculate K times N sub T times W sub T. Okay, this will give us what? Will give us the total production capacity that this company can produce, okay, in each month of the planning horizon. Because remember, K times N, here K times N is what is the quantity that can be produced by 1 worker in a month, which is 3.75. So 3.75 aggregate units can be produced by a worker. When we multiply 3.75, okay, by the number of workers in a given period, this will give us the total number of aggregate units that we can produce in that month. That's the production capacity. Now, this number does not have to be an integer. Remember, after all, we are talking about aggregate units of production. Aggregate units of production may not be integers. Right. So that's exactly the total quantity that is available that we can produce in regular time production. The next now comes the question of, well, how many aggregate units shall I produce in each given period? Okay, such that I do not exceed this quantity, which is the capacity available in regular time production, and I can actually fulfill the required demand throughout the 12 months. Okay, so let us see here. Now, in order to do that, remember the summation of the total demand that we have here in our model. Okay, if you sum up the values here, let's see, it equals sum. So it's 240, right? So if we are talking about 240 units, total aggregate demand units. If you divide this number by 12 months, then this means your production, okay, can be simply maintained at 20 units per month. And this should be enough for fulfilling the total demand required, because at the end, the summation here is going to be what? Is going to be 240. Okay, and remember, of course, we do not have any initial inventory value, and of course, we do not have any backlogged quantity. So in this case, okay, maintaining a fixed level of production of 20 aggregate units per month will fulfill the required total demand throughout the planning horizon. Now, if we decide to do that, maintain that fixed level of production, this means, okay, we will not have an overtime production in any month, and we are going to have undertime production of 2.5 aggregate units, which is simply the difference between this number, okay, which is the available capacity, the total number of aggregate units that we can produce, and the quantity that we decided to produce in a given month. This difference will give us the under capacity, the unused capacity, expressed in terms of the number of units. Next, we need to calculate both the inventory and the backlogged quantities. And remember, we have a restriction on the backlogged quantities because it cannot be non-zero value. I mean, it cannot have a positive value. This is, of course, a restriction given in this problem, specific problem. Now, let us see how we calculate the inventory. It's mentioned that the initial inventory and backlogged quantities are zeros in the beginning of the planning horizon. So when I need to, the formula used here to calculate the initial inventory or the backlogged quantity is simply the inventory balance equation. And here what I did is I have interpreted the inventory balance equation using Excel. So it's basically here, the value in this cell is the inventory at the end of the first month. This equals what? This equals the inventory at the beginning of the planning horizon, okay, plus the backlog, minus the backlogged quantity at the beginning of the planning horizon. Both are the zeros, but I mean, I just used the formula as is. And then we, of course, add the production quantity and subtract the demand. That's basically the formula that I have used here. But then when I do that, remember, sometimes in some periods, the demand might be higher than the production capacity, right? So what shall I do in this case? Well, in this case, since we have already decided to maintain a fixed level of production, and the company policy does not allow any backlogged quantity, then in some periods in which the production capacity and the available inventory in the previous period. So let's take this case for instance. Now, here, this specific case. Okay, here we are talking about what? The production capacity, okay, that's available in the 6th month is 20. The inventory at the end of the 5th month is 5. So this means I have a total quantity of 25 units available, okay, to fulfill the required demand in month 6. But the demand in month 6 is actually 35, which exceeds both the available capacity and the inventory. So in this case, since I'm not allowed to have backlogged quantities, I shall have some subcontracted quantities. Since subcontracting, of course, is allowed in this problem, so definitely the difference between 35 and 25 is 10, and that will be our subcontracted quantity. Again, remember, in this problem, the company has a policy not to have any overtime production as well. So if this policy is not there, then I might allow some overtime production here. All right, someone might say, well, why don't you produce more quantities in the previous periods in order to fulfill this difference, which is 10 units? Well, you might do that as well. So someone might say, well, my production is going to be, instead of 20, exactly 20 aggregate units, I will choose to produce 22.5. Well, that's fine. So if you put 22.5 in the first 4 periods here, you will at the end have probably the 10 units, the 10 aggregate units fulfilled. So you do not need to subcontract. But in this case, you will have extra inventory kept. Okay, and at the end, it's about costs. If you keep some units in inventory, this will cost you inventory holding cost. If you use subcontracting, this will cost you subcontracting costs. So it's you need to have a balance between both costs. See which one will give you the lowest cost and you should choose. But for now, for the current application, well, I decided to have a fixed production quantity of 20 aggregate units throughout the planning horizon. And any excess demand requirements will be fulfilled by subcontracting. Now, you continue the calculations similarly. Okay, let us see here. For instance, for these periods, 8 and 9, as you can see, we reach the situation in which the demand is exactly the same as the production capacity in the given period. So we end up not having any inventory or any subcontracted quantities. Now, at the end of the planning horizon, the last 3 periods here, you see the demand started to be lower than the available production capacity. So this will mean this means what? This means you are going to have inventory kept, and as a matter of fact, you will end up having 15 units of inventory kept in at the end of the planning horizon. And again, these 15 units will cost you money. Now, as you might see here, this 15 is exactly the same as the number of subcontracted units, which actually did in periods 6 and 7. So this now is an application of the level strategy in which we try to maintain a fixed workforce level throughout the planning horizon. And we also try to maintain as much as we can a fixed production quantity level. Okay, and we play with the other decision variables: how much to keep in inventory, how much to subcontract, and so on. Now, next, we need to calculate what? We need to calculate the associated costs of this plan. So total hiring cost is now 3,000. Why? I simply multiply the cost of hiring one worker by the summation of the values given here in this column. Okay, this will give us the total hiring cost. Similarly, the total cost of firing workers is the multiplication of the firing cost per worker times the summation of the values given in this column, which is 0 in this case. Total inventory cost is calculated by multiplying the inventory holding cost per unit per period, okay, C sub H, times the summation of the values in this column, okay, which includes the values of the I sub T variables. And next we calculate the total regular time production cost, which is simply the multiplication of the regular time production cost per unit times the number of units produced, which is the summation of the values given in this column. And then we calculate the total overtime cost. Of course, we know that we do not have overtime here in this solution. So again, we sum up the values in this column multiplied by the cost of overtime, which is not allowed in this case. So I put the cost of overtime equal also to 0 because it's not allowed. Total undertime production cost, now again, it's the undertime cost per unit times what times the summation of the values in this column. Okay, this represents the unused capacity, the cost of unused capacity. Then finally, the total subcontracting cost is the summation of the values given in the last column for the variable S sub t times the cost of subcontracting 1 unit. Okay, the summation of these values will give us this number, which is the total cost of the current solution using the level strategy. So that's basically the application of the tabular graphical approach using the level strategy in this problem. Now let us have a look on how the chase strategy would attempt to solve this problem in a different approach. Okay, I have another Excel sheet here for the application of the chase strategy. It's basically the same problem data that we have presented. Okay, and in addition to that, actually, we decide on how we are going to calculate the number of workers in a given period. Because here in the chase strategy, okay, this strategy works by looking for the number of units demanded in a given period, and then based on that number, I calculate the required number of workers that can fulfill that demand. And from that, of course, we calculate the amount of production, and then we decide if we need to probably have some subcontracted quantity or overtime. Of course, we do not have overtime in this example, but I mean, generally, that's what we do. So here I entered the formula actually that I'm going to use to calculate the number of workers in a given period. It's simply, I take the ceil function. The ceil is actually what the nearest higher integer value for the multiplication of d sub t, which is the demand in a given period t, times 40. 40 is the production man hours per unit, and then divide that by 150. 150 here is the number of monthly working hours per worker, which is basically simply multiplying 3.75 times d sub t. So this is how I calculate the w sub t. Now, if we go back now to the table in which we give our solution, as you can see here, in this column, okay, I have a calculation for the number of workers in each period using the mentioned formula. So in the first period, for instance, we need 5 workers according to the formula. Next we have 4, 4, 6, 8, 10. Oh, we have 10 workers demanded in period 6, and then we continue until we reach the last month. So that's the formula that we have applied to calculate the required number of workers. Now, based on the value of W sub t, I calculate the number of hired and number of fired workers accordingly. And the formula is straightforward. Here, the number of hired workers is the difference between the number of workers in this period, in a specific period, and the number of workers in the previous period. And of course, if this number is negative, then the value of h sub t should be 0, okay? Because we cannot have a negative value for any variable. And of course, it does not make any sense, all right, to have a negative number of hired workers. So here, I use the function max, okay, the function max to represent this relationship. So it's a maximum of 0 and the difference between these two values. The opposite now is for the number of fired workers. It's the maximum of the difference between the number of workers in the previous period and the number of workers of the current period and 0. Okay, so we repeat this formula for the 12 month, and these are the numbers that we have obtained of the number of hired and fired workers. Next, based on the calculated value of W sub T, I calculate the production capacity, which is K times N sub T times W sub T. And again, this represents the total number of aggregate units that is available for that is made available in each month by the number of workers that we have decided. Now, accordingly, based on the available capacity in each period, I have to make a decision regarding the production quantity. As you can see here, for the first period, the total quantity that I can produce is 18.75, which is actually more than what's demanded in that period. So in this case, okay, I will decide to produce only the required demand. So the idea of the chase strategy is basically changing the production capacity level, okay, to match the required demand. So at the end, the production quantity that you are going to put here in this column is actually what is actually the demand, okay? But then you will have a difference here between the available production capacity in units and the amount that you will decide to produce, and that of course will appear in the column of U sub T, which is the underproduction value. So if you follow this chase strategy, as you can see, you will not have any inventory value, neither backlogged value, neither subcontracting value. So basically you are producing what is exactly demanded. And of course, to achieve that, we dynamically change the number of workers in each period. Now, similarly, just like what we did before, we calculate the total costs associated with this plan. As you can see here, the cost of hiring and the cost of firing, are relatively very high values here, okay, in this solution. While in the other side, the inventory cost is 0 because we do not hold any inventory in this solution. The total regular production cost is again the summation of the values of given in this column, okay, P sub T by the production cost per unit. And of course, we do not have overtime cost. We have undertime production cost for the unused capacity, and the subcontracting cost is 0. Now the cost is 246,500, okay, which is compared to the level strategy is actually what, let's see here, the level strategy, the cost is a little bit lower than actually the chase strategy. So as you can see here, if you compare these two different strategies, okay, you can get a sense of how they actually work. Here, the level, as you can see, works on minimizing the total costs of hiring and firing, okay? While on the other hand, you have to keep something in inventory to fulfill the required demand in the periods in which the demand is higher than the available production capacity. While on the other hand, the chase strategy maintains or tries to maintain 0 inventory as much as you can, okay? And on the other side, you have costs associated with high cost for hiring and firing workers. So these are basically the two extreme solutions that you can get for this problem. Now, we are going to have a look on the mixed strategy to see how it works on the given data. Well, when you apply the mixed strategy, as I mentioned, you need to look at the shape of the demand to see how the demand is actually changes with respect to basically the the cumulative production level. And this actually, in order to do this efficiently, you might wish actually to represent or to draw the data that represents the cumulative demand. I'm not going to show that to you. You can do it, of course. It's easy. But the idea is you are trying to come up with a shape that gives you insights of how the demand, or what are the periods in which the demand is relatively low, and what are the other periods in which the demand is relatively high. And the comparison here is usually done with the level strategy, in which you maintain a fixed level of production. So let me go back to the slides and see, recall the figure that we have seen there. So it's yeah, here is the figure that I talk about. So as you can see here, okay, the idea of the chase strategy, if you follow the chase strategy, you would get cumulative production that actually coincides over the cumulative demand curve. If you follow a level strategy, that's what you will get, a straight line, because you have maintained a fixed production quantity throughout the planning horizon. Okay, now for the mixed strategy, okay, you need to probably divide your planning horizon into sub periods. Okay, for instance, here, if you have a curve that looks like this one, I might think of, well, in the first probably 4 periods here up to this point, the demand is relatively low. So probably, okay, I can actually have throughout these 4 periods a fixed workforce level, which actually follows the idea of level strategy. But the number of workers that I'm going to allocate here is not actually the number of workers that I need to maintain the fixed production capacity in the level strategy. I might need to use lower number of workers for the first 4 periods. And this will suffice for fulfilling the required demand throughout the first 4 periods. And then after that, you can see the demand is higher in the last 2 periods. So what I'm going to do is, well, in that case, after the 4 periods, the first four periods, I'm going to increase the number of workers, okay, and maintain that number fixed for the remaining 2 periods. So the idea of the mixed strategy, it's like you are mixing both strategies, level strategy with chase. But you are not chasing on the level of the period itself. You are chasing on a number of periods. And when you have a level production by fixing the number of workers, you do that for a number of periods as well. So that's the basic idea of the mixed strategy. So let me go back to the Excel sheet and see how it's applied to the given problem. Well, basically, based on the given data, well, I thought, well, I can actually divide my periods into 2 6-month periods. So the first 6 months will represent the first interval in which I wish to maintain a fixed number of workers, fixed level of production, okay, and the remaining 6 periods will form the next uh, uh, interval in which I would wish to maintain a fixed number of workers or fixed level of production. So in order to do my calculations, I need first to calculate what? To calculate the average demand in the first 6 periods and the average demand in the next 6 periods. So the average demand for the first 6 periods is 21.67. Now, based on these numbers, well, the number of workers that I wish to maintain in the first 6 months would be 6 workers. Okay, why? Because actually, apparently, the demand in the first 6 months is relatively higher than the next 6 months. Now, I do the same for the next 6 months, and I find that the number of workers, the 5 workers, would be sufficient for fulfilling the required demand. Right? Now, based on these ideas, if you compare the values of the WT variables with the level strategy, let us go back here. Well, the level strategy, when we calculated the number of workers, we found out, well, it should be 6 throughout the 12 months, right? That's what we did here for the level strategy. But in the mixed strategy, well, no, it says, well, you can have some changes in the first 6 months. Okay, I will keep it 6, and then the next 6 months, I will have 5 workers only. Okay, now this will have an effect, of course, on the number of hired and number of fired workers, definitely. Okay, and of course, this appears in these 2 columns, as you can see. Now, again, we calculate the production capacity available based on the number of workers. As you can see here, we have changes happened, okay, compared to the level strategy. And then we will make a decision of what would be the production quantity, okay, based on the available capacity. So in this case, as you can see, well, since the number of workers in the last 6 months will be less, then we might think of, well, we need to keep more inventory, okay, throughout the first 6 months. And to do that, actually, I decided to have a production capacity as high as possible. So I decided to have it 22. Of course, again, you can have it 22.5. That's fine. But I decided to have it 22. Now, if I do that, then this means I will have a minor undertime of 0.5. And of course, I will have excess inventory, okay, that is going to be used in the future. Okay, now after the first 6 months, in the 7th month, the production capacity will be less, and the production quantity, I decided to have it 18. So the total undertime, that we will have also some undertime. We will have also some inventory, and actually we would need to subcontract some quantities. Again, we have subcontracted here 9 units, and again the 9 units will go back here at the end of the planning horizon. Of course, I mean, you can have changes to, this solution. You might think of, well, I don't need to keep inventory. If I wish not to keep any inventory at the end of the planning horizon by having a zero value here, then this means, well, I can reduce my production in the last 2 months, okay, or at least in the last month, instead of producing 18 units, I might produce only 9 units. I mean, you might have some alternative solutions, okay, based on the chase strategy. The mixed strategy. So, for instance, if you wish, you can reduce the number of workers again in the last 2 periods, for instance, okay, because we have really excess inventory. So, somebody might say, well, I might have only 4 workers here, okay, and then in this case, you don't have undertime, okay, so your undertime will be 0. Okay, and of course, this means your production is going to be exactly 15, for instance, here. Okay, and again, 15 here. So this will reduce the inventory at the end of the planning horizon, while maintaining, a level production for the last 2 months. I mean, I can change my plan as such. Well, let's see here. The total costs associated with the mixed strategy is much less compared to the chase and the level strategies. And again, remember, what we are trying to do here is we are trying to have a plan for our production that minimizes the total cost. The level strategy and the chase strategy are simply the 2 extreme solutions that we might get for this problem. when we apply very extreme ideas of how to handle the capacity versus the demand. And the mixed strategy is something in between that tries to achieve lower costs by combining some ideas from the chase and the level strategy. All right. So next, we are going to see how to apply or how to use a very nice tool in Excel, which is called Excel Solver, to solve this problem. And this is going to be the next part of this lecture.